Yeah, great. Thanks a lot to all the organizers for what's been pretty stimulating meeting so far. And I guess as we had some great motivating talks this morning about the need to make planets and about the disks that they're forming in. And so my job here is to start to delve into the theory of the actual mechanisms by which planetesimals form. And the choice of a smaller font size for large cores is not an accident here. There's lots of subsequent talks that are going to deal with the growth past the planetesimal stage, so I'll have some relatively brief comments on that. And let's see, so I already got some grief from Hal that I'm calling Pluto a mere planetesimal. Okay. So, but I was going to say, this has obviously been a great year for flying by and flying near the minor planets in the solar system. Ceres here was found to have these intriguing dots inside its crater. So Ceres at about a 500-kilometer radius is actually about the size of things we think we can make by the planetesimal formation mechanisms I'm going to talk about. Pluto at sort of 1,200-ish kilometers is a bit bigger, so it probably had a bit more growth that went on afterwards, and as we now know, also has a lot more geologic activity than we expected, which is pretty exciting. So the last thing I was going to say on this title slide is that while this introductory talk is going to be, it's fairly conceptual. I'm not going to hit you with too many equations. If you do want to learn more about how things work, obviously the hands-on sessions are going to help with that. But there's also some review articles you can go through to get more detail and learn more about how to calculate things. And one of those review articles is one I wrote with Scott Kenyon a couple years ago that covers various aspects of planet formation, including planetesimals. So again, this is sort of, an exoplanet themed and organized meeting. And now the slide advances. Yay. Okay, so yes, obviously this is an exoplanet themed meeting. And in terms of the clues that we've gotten from the exoplanet discoveries about how planets actually form, probably the biggest clue has been looking at looking at the metallicity of the host stars, right? And so the clue that's been around for a long time and continues to hold is when you look at some of the first exoplanets that were discovered, the giant planets that were discovered by the radial velocity technique. If you look at the metallicity of the host stars, you find that the fraction of stars that host a giant planet rises dramatically with the metallicity of the host star, with the solar metallicity as with Fe over H as a proxy, is right here. So the supersolar metallicities really have an advantage in terms of forming giant planets. And it turns out so do there's also a stellar mass effect here, and that the more massive stars also have a preference for forming giant planets. And so here the idea is that both it's the total amount of mass in your disk that matters, that's thought to correlate with the mass of the host star, but it's also crucially the amount of solid forming metals that you have in your protoplanetary disk is key for forming giant planets. And then it's key for giant planets is particularly interesting because we know terrestrial planets are made of rocks, but giant planets are made mostly of gas, right? And so there's been sort of an interesting sort of both confirmation and twist on this that's come from the Kepler data. Where here there's a couple different things being plotted here. First you have in your histogram here is just showing, as of the date of this paper, the planet counts in different size bins. So your sort of Jupiter-sized planets are here at 10 Earth radii, and then as we know, most of the planets found are these super-Earths. But then also plotted for each bin is what's the average metallicity of those stars that have these planets. And so again, we see that the giant planets have this bias towards high metallicity. But curiously, the sort of super-Earths and low-mass planets that we think are primarily made of solids, those don't have as strong a bias of having solids. So that's particularly interesting, right? Because that suggests that you need this metallicity advantage to really get the core formation going, get it going early, to be able to then go all the way to make the giant planets. And so that really argues that this initial step of getting your solids into planetesimals is key, not just obviously for making minor planets, but for making giant planets as well. And so indeed, we can make sense of this through what we've already heard about through the dominant paradigm for planet formation, which is the core accretion model. And we can then go and break it into the different stages. And again, the one I'm going to focus on here is the stage of growing from the small dust grains into planetesimals. And from there, we then know we need to grow into larger terrestrial planets and cores. And if that core grows large enough while the gas disk is still present for the several mega years on average that we heard about from Jenny, then that massive solid core can accrete a giant envelope. And then, of course, as I think we're going to hear more about from in Richard Nelson's second talk, is that these planets don't necessarily stay put as they're forming, and that they move all about, and that's obviously useful for understanding the demographics of where the planets currently reside. So, just in case you weren't yet convinced that planetesimal formation was an important part of the game, so Scott actually warmed me up nicely as he had a lot of these numbers here of how many orders of magnitude in mass you have to grow to form a planet. But it turns out most of those orders of magnitude are in the planetesimal formation process. Overwhelmingly, the most of them, going from dust grains to planetesimals, involves well over 10 to the factor of 10 to the 30, more than 30 orders of magnitude. Whereas then going from planetesimals to giant planets is it's not even 10 orders of magnitude in mass. That's nothing. So okay, now we have finally getting to something approximating an outline here. What are some of the key ideas I want to talk about in terms of what you have to do to make planetesimals? And the keys are that you're starting from dust grains and very small solids, and crucially those are embedded in a gaseous disk. So okay, one of the aspects of being small is that a small body doesn't have very much gravity, right? So that means the accretion process is very different from having two big planetesimals smack into each other, and then you can reaccumulate all your fragments gravitationally. Now, for these small grains, if you want them to stick, then, well, they actually have to stick by sort of surface coagulation forces, which are primarily electrostatic in nature, not gravitational. And the other aspect, again, that's crucial is this all has to be done in a gas disk, right? So you get rid of the disk before your solids have grown. You'll get rid of the solids along with it. And then obviously you want to make gas giants as well, at least in certain regions. So you have to do this all in the presence of gas. And gas exerts gas drag on solids, which is a crucial dynamical effect for small solids, as we know when we look through a sort of sunny window on a dusty day. It's the small grains that are much more easily held aloft by drag forces. And one of the main effects of this drag is something we already heard a question about earlier today is, what about this meter-sized barrier that's caused by the radial motion and migration of solids around that size? And the sort of resolution to these issues that we'll get to is that you can concentrate these particles in a gas disk to the point where they gravitationally collapse. So we've got a lot to talk about. And so let's start with the radial drift issue and how that leads to this meter-sized barrier. So like planets, the dominant force on the gas that's in a gas disk is gravity, mainly the gravity of the host star. But there's another force that's a fraction of a percent of that, which is the pressure gradient in the disk, right? That the disk is hotter and denser in the inside than the outside. So there's a pressure gradient that pushes out. You can think of that as effectively weakening gravity a little bit, and so that means the gas rotates a bit slower than a planet would want to on average. It's sub-Keplerian rotation. Okay, so the amount of that sort of is set by the temperature of the disk and the things that we sort of know something about from disk observations and from radiative transfer models of whether the disk is flat or flared and all of that. But the speed is on average about 50 meters a second. So that's much less than orbital speeds. But it's not nothing. You get a speeding ticket for going at that speed, right? So the question is, what is the effect of that on the solids in a gas disk? And well, that's very size dependent, right? So if you're talking about a tiny dust grain, again, the effect is that these grains are so small, the aerodynamic coupling is so tight that the gas just drags just basically slows the dust grains down very efficiently, sort of drags the dust with it, so that dust doesn't see very much of a headwind, right? But to the extent that it does see a headwind, and all the particles will see some headwind on average, that headwind robs these particles of angular momentum and causes them to drift inwards, right? So I've already explained then why the dust grains have sort of slow drift speeds, because they're tied to the gas. If you get all the way to planetesimal sizes and larger, right, now these things are plowing through the gas full speed ahead, and they're seeing this 50 meter a second headwind, but they've got so much inertia, they've got such a head of steam, the drag is a sort of a small correction to that, so they lose just a little bit of angular momentum per orbit, and they drift in very slowly. So then there's a sweet spot here, which is sort of around meter sizes, hence the meter size barrier, where the drag force, the ratio between the drag force and the inertia is optimized, and so you see about a medium speed headwind, but then you drift in at the fastest possible speed, and it turns out that drift speed is the same as the headwind speed of about 50 meters a second, and if you just think of what that means, convert your units, 1 AU at 50 meters a second, you'll fall into the star in only 100 years. And this is a dramatically fast time scale compared to growth processes, compared to the million-year lifetimes of the protoplanetary disk, so it's a big deal. So what is it that sets the meter size as being special? So what matters is this so-called stopping time scale, the aerodynamic time scale of the particles. It's just the time, if you have a relative velocity between particles and gas, what's the time to exponentially damp that relative velocity. So the absolute time scale is not what matters. It's the ratio of that time scale to the orbital time scale, right? Like sort of a year, 2 pi over a year at 1 AU. Okay, so then this number, the ratio of these two, if the number is small, that means the aerodynamic coupling is very strong and tight, like it is for micron-sized solids, whereas if this number is large, that means drag is a weak effect, like it is for kilometer-sized planetesimals. And then the optimal coupling regime is when this number is about 1. And so again, it's for things that are around a meter in size, or actually a bit less than a meter in size, in sort of the inner disk, around sort of 1 AU-ish type distances. Those are the sizes that are optimally coupled. But then because gas densities are lower in the outer disk, the gas gets more tenuous, then it turns out that things that are in sort of the several millimeters to several centimeter range, that those are the objects that are marginally coupled in the outer disk. And so here then, this is looking at this radial drift time scale, just sort of, right, the time scale it takes to drift your current orbital distance. That this drift time scale, there's the speed limit here, the fastest possible you can go is for optimal coupling. And again, in the inner disk, the meter-sized objects are going close to that maximum speed, and that time scale is indeed about 100 years. You can, again, get very fast drift of millimeter-sized even solids in the outer disk, and a lot of these drift times are much faster than the disk lifetime. So this is something we have to grow through very quickly, but see if we can go through very quickly, we both have very slow drift of the micron sizes, and then slow drift, at least outside of 1 AU, of the kilometer-sized objects. So how do we want to do this growth, right? So there's a lot of different growth processes we've already heard that to climb this ladder, which is a ladder both in size and again in the strength of this aerodynamic coupling. And so very broadly speaking, there's sort of two sort of classes of growth. You can think of bottom-up growth, which is taking small grains and sticking them together to gradually get larger bodies. That's often thought to be the only thing that happens in sort of the growth of solids. But actually, it's now thought that top-down processes are very important, that taking your sea of small bodies, collecting them into dense regions by a variety of mechanisms, and then ultimately having them collapse on themselves gravitationally. This is, again, more of a top-down type process, that this is important for the final stages of planetesimal growth. So starting with the sticking, that's again crucial for dust grains, and as we heard, something that's actually observed to happen in T-Tauri disks, the growth up to millimeter sizes. Beyond millimeter sizes, it gets harder to study observationally, but it can be studied in laboratories, and particularly you want to study it in a microgravity environment to mimic what happens in space. And so there are these drop towers where people take their experiments and drop it for about a second and do their experiments very quickly and measure whether things stick or fragment. So it's been known for quite a while that it's actually a big problem once things get beyond millimeter sizes for objects to stick. And sort of from a whole host of experiments, there's been sort of work done on what is the boundary between different behaviors of objects sticking together. Sticking generally happens if objects are low in mass and they collide at low velocities. Notice these are velocities. This is sort of meter per second. These are the sort of tens of meters, 50 meters per second speeds we're talking about for drift, or what, well here in this problematic fragmentation regime. And the sticking regime is also, again, restricted to very low masses corresponding to very small sizes, well below a centimeter. And then, there's other issues that, okay, what if, we're in this low gravity environment. This is a space shuttle experiment that was done, that when you're in a low gravity environment, if you have a cratering type event, you might accrete this projectile, but then you might blow off more mass in your crater. So there's a whole mass balance argument to do. But then there's this argument that, okay, even when you have fragmentation, you might get a bit of mass transfer. So I want to focus on this experiment because it's particularly interesting because it's right at this problematic size of, can we, this key question, can we grow by sticking to centimeter sizes and beyond? And so what this plot is showing here is that when they have these fragmentation events as a function of the collision velocity, what is the ratio of your largest final fragment to your initial size? And so you see for low-speed collisions, it's basically all these bouncing events, right? This ratio is just 1. They just bounce off each other. There's no mass change. Then as the speeds, still very low speeds, as speeds get above about 10 centimeters per second, or 20 centimeters a second, you start getting a combination of behaviors where you get fragmentation, but then you can also get a small amount of mass transfer. And I want to emphasize the small amount here, that there's different scales here on these axes, that once you get at sort of even tens of centimeters per second, you're getting catastrophic fragmentation, whereas the amount of mass transfer you get is typically under 1% mass growth. So that the fragmentation is winning by a lot. And again, these speeds are still very low. These are tens of centimeters per second compared to the drift speeds of 50 meters per second. And then turbulent velocities, which we heard about in Richard's talk, are going to depend on your local effective value of alpha. But those can easily exceed tens of meters per second as well, and can even be well above a meter per second in dead zones. So sticking is very important, but unless you're very optimistic about how it works, it's probably not the whole story. So we want to think about ways of concentrating particles in disks. And it's interesting that the idea of concentrating particles in disks has been around obviously for quite a long time. This is the Edgeworth who was one of the first people to hypothesize a Kuiper belt. And I thought in addition to being a cute old-timey plot, it was sort of interest to me that a British retired lieutenant colonel was actually thinking about planet formation during the during the height of World War II. So it shows what a sort of powerful idea and problem this is, that even when the world is going crazy, we can think about planet formation. But in terms of making these condensations, he actually didn't have a lot of the specifics worked out yet. And so currently there's a lot of ideas out there, and I've sort of broadly grouped them into 3 different categories that I'll sort of explain what they mean. So the first idea is sort of static concentrations means you're collecting your particles in some long-lived structure in the gas that has been formed by some other mechanism. So the simplest example of this is a simple axisymmetric ring which creates a pressure maximum. So again, the reason there's radially inward drift is because you have a pressure that decreases outwards. If your pressure increases outwards, then you actually have particles drifting outwards by the opposite argument, and so particles will obviously collect naturally in any pressure maximum. And then a slightly more complex variation of that is if you have an anticyclonic vortex, which is the only kind that might be stable, that those are pressure maxima as well, in which particles can drift and concentrate. And as we see, there's been some speculation about whether ALMA is now actually seeing, not speculation, there's actual observations here about whether we're now seeing these non-axisymmetric or in some cases axisymmetric concentrations of dust. So what might the sources of these rings be? We heard about this some in Richard's talk. There's anytime there's a transition in the accretion efficiency of the disk, you might be able to create a mass pileup. So this could exist at dead zone boundaries. Snow lines might possibly be another cause related to that, because of the ionization efficiency with and without ice. The zonal flows are a phenomenon that can exist in MRI turbulence. Spiral arms that occur very early in the lifetime of a protoplanetary disk are not quite axisymmetric rings. So there's a lot of ideas out there, and it's not clear which of them will work, which will be robust, which will last long enough to make planetesimals. And also intriguingly, whether you actually need a planet in the first place to form these vortices and rings, in which case, obviously, there becomes a chicken and egg problem if you're relying on this process to make your planet in the first place. So what else is there? So passively dynamic. That sounds like a contradiction, but what I sort of mean is that you have now the gas is much more dynamic because it's turbulent, but the particles are responding sort of passively as test particles. And so a common everyday example of something like this are sort of dust devils, where you sort of see on, usually on a hot day, the ground heats up, there's some eddy or whirl in the ground, and it can collect leaves or trash or sort of anything. This is actually a bit different than what I want to talk about, because this is sort of, again, it's sort of a boundary layer thing, and you have a big upwelling of gas, but it's pretty, and we all know what it is. But what's actually thought, the process related to this that happens in disks is a bit different. Instead of the particles concentrating in an eddy, what happens in more isotropic turbulence is, turbulence is, you can think of as a superposition of lots of different whirling eddies. And what happens is that the particles are actually centrifuged out from those eddies. So they're pushed preferentially into the interstices between the turbulent eddies. And so this is an idea that came about in the fluid dynamics literature a while ago and has sort of recently been applied to, can this concentration of particles cause the formation of planetesimals? And so there's actually, a fair amount of conflicting result in the literature because these eddies overturn so quickly and on such small scales. Can you actually produce concentrations that are long-lived and massive enough to form planetesimals? So these authors make some assumptions that say yes. These authors do detailed simulations and say no. And then this author makes different assumptions and says, well, it actually happens differently. So it's not clear. Let's see. But the one thing to say here in general is that this idea of turbulence concentrating things is a bit right. It's a bit of sort of a double-edged sword, which is what this is supposed to remind me of. Because one of the ways we think of turbulence is this agent that stirs dust, and it just sort of sends it scattering in all directions. And so turbulence does actually have this double-edged nature, that on large scales it can send the dust all over, but on small scales it can produce these concentrations. And it is the sort of competition between these two effects that requires a lot of careful work to understand how it happens. So, but the next concentration mechanism is more of a more completely active sort of spontaneous concentration mechanisms, which we can make an analogy with sort of birds that sort of flock together as they migrate. So this is clearly an aerodynamic effect. The birds sort of decide to cluster together so that they can change the flow of gas around them. And now dust grains in a disk clearly aren't sentient creatures like birds, but they are able to interact with each other and interact with the gas by the nature of drag forces. And that basically there's a feedback effect, that there's less drag on them when they cluster together, even when the dust grains cluster together, just like the birds. So okay, so this effect has a name. It's called the streaming instability. This is when particles trigger their own clumping by means of a hydrodynamic instability, a coupled particle and hydrodynamic instability. And so even though the behavior is fairly complex, it is something that arises from very simple ingredients, right? They basically, like I said, the main thing you need, and so this is from the original linear treatment, discovering the instability, is that you model your particles as a fluid here, and you obviously have your drag force here that's acting on your particles. And then the key ingredient is that you also have a back reaction that obeys Newton's third law. Obviously, that momentum that you take from the particles goes to the gas. And then the other key ingredient is just this pressure gradient, right, that acts on the gas, that drives the radial drift, that's also the same energy driver for this instability. Now, when you do simulations of this, it's a small-scale process. So you don't tend not to model it in the whole disk, but in a local box. And when you do a simulation, you don't have to make a fluid approximation for the particles. You can include actual particles, although they're superparticles, because you can't include the total number of them. Each particle represents many actual ones. So okay, so this is now a movie of the sort of simplest version of the streaming instability, where you'll see here the particle concentration. It starts with the radial drift. Particles are drifting in. The initial scale here is predicted by linear theory, but then the particle concentrations are quickly going nonlinear. The sort of light-colored regions are the most dense. The black regions are the voids. And these are for optimally coupled, stopping time, dimensional stopping time of one solids that drive very strong particle concentration and some vertical motion. Now, this instability, or in this simulation, you notice it's sort of periodic in the vertical direction. There's sort of no vertical gravity keeping things in the midplane, but that is now corrected in these simulations. And so with once this vertical stratification and particles settling to the midplane is included, we can now look at what are the actual conditions we need to have these particle concentrations be strong. Well, the first, is probably not that surprising again, since I've been emphasizing it. It's you need particle sizes in this optimal coupling range. So maybe they can be lower than 1, maybe they can be 0.1, but if you get much smaller than that, the other side of the double-edged sword starts killing you, and the things are just stirred out of the midplane too efficiently. The other factor that matters a lot is that you need to have enough solids relative to gas. Again, this is a feedback effect. The particles have to affect the gas dynamics, so there have to be enough of them. And so it turns out that amount is about what we think we have at solar abundances. It's something a bit bigger than 1%. So maybe you need a bit of enrichment, but it's about in the range of what we think we might be able to create. And so here in these simulations, you're seeing the difference is you have, if this ratio in this sort of local global ratio of 1% in your box, that once they settle to the midplane, if you only have 1%, you get sort of weak particle concentration, whereas if you get to 2%, that particle concentration becomes much stronger. And you're seeing here in this radial distribution is the sort of inward drift of these clumps as it grows more and more strongly in time and then stops drifting in quite as fast. And so exactly what this number is does depend on the strength of the radial pressure gradient, but the idea that there is a metallicity threshold is something that obviously is interesting in light of what we know about extrasolar planet abundances. And I'd like to point out that there's also a poster by Arizona second year now graduate student Ershin Lee on trying to understand these thresholds and other issues in more detail by studying some of the important numerical effects of the simulation box size. This is only going to 0.1 scale heights in each direction, which isn't quite enough. So we're trying to do better than that. So okay, but the whole point of this is that when you get to these very strong particle concentrations, which again can be well over 1,000 times the gas density, so strongly gravitationally unstable, the point is you then collapse to form planetesimals. So with this movie, which is done by Jake Simon, with Athena now including the self-gravitational interaction of all these particles, we're starting with this ring that was created by these streaming instability effects. And once self-gravity turns on, this ring sort of rapidly fragments into a population of gravitationally bound sort of proto-planetesimals, and these then start accreting mass from the ring, and then also their individual gravity starts becoming strong enough that they can scatter each other, and some of them leave the ring and then stop growing, and so then you wind up with a sort of broad size distribution of planetesimals. But the largest objects you make, they don't actually collapse all the way to solid densities in these simulations, but the amount of mass in them is equivalent to objects that are 100 kilometers or even several hundred kilometers in radius. So quite large planetesimals can be made this way. So the key issue then is that, well, we still have this problem that of these bouncing and fragmentation barriers, right? We want to grow to these sizes of tau s of sort of 0.1 at least, but that's still sort of, 10-ish centimeters maybe at 1 AU. And, okay, maybe in the outer solar system you don't have a problem, but in the inner solar system you do have a bit of an issue. So one way to get around this, maybe in the inner solar system this works, if you actually get rid of the gas, then actually you can increase these stopping times. It's sort of like you mimic the outer disk conditions in the inner disk. That's, maybe that sounds like cheating, but if you don't need to make giant planets, it's possible. And the other is that we need to, take a closer look at how, at these other mechanisms and how they may interact with the sort of active dynamics of the streaming instability, the pressure bumps, and then actually taking a look back at the old idea that self-gravity is actually important from the beginning. Right? Now, normally, before you concentrate particles, the idea is that, densities are too low for direct gravitational instability to be relevant. But there's actually a mode of slow gravitational instability called secular gravitational instability that gradually collects particles into rings by transferring the excess angular momentum to the gas. So this is a process that's so far been studied analytically. It's difficult to study numerically because it involves fairly large length and time scales to get all the physics in. We're 5 minutes? Oh, good. Okay. And so this makes it hard to do detailed simulations that have all the different components involved. But there's also an opportunity here, because an instability that actually takes place on large scales and grows slowly is something that you actually have a chance to observe. And so indeed, there's been sort of speculation by these authors that the sort of structures that are being observed in disks by ALMA, either the sort of individual rings, or perhaps even that I showed before, or the multiple rings like we're seeing in HL tau, could be caused by these sorts of dust gas instabilities. Obviously, lots of other people have lots of other interpretations for what could form these rings as well. But in terms of the general picture of, okay, however it is that you create overdense concentrations, or however it is, right, that you trigger the gravitational collapse, there's some evidence from looking at bodies in the solar system that a collapse mechanism is responsible for making solar system planetesimals. So one of the key things you can do is you can look at the most pristine population of planetesimals that we have in the solar system. That's the cold classical Kuiper belt. There's a remarkably high binary fraction of sort of roughly equal mass, equal size, sort of 50, 100 kilometer binaries. There's a broad range of colors of those KBOs, which are mostly binaries. But if you look at the primary and secondary, the colors match. So that suggests that those objects, it wasn't just two random planetesimals that captured each other. There's an explanation due to David Nesvorny, which is consistent with this collapse scenario, that you had an original cloud of dust, and as it was collapsing, it had too much angular momentum to collapse into a single planetesimal. So it split the same material into two objects, and because it came out of the same hunk of material, these objects have the same colors. And there's another argument which is new and which I particularly like, and it comes from the very simple observations that comets have tails. And that's the fact that comets can outgas tells you something about the material strength of comets. And so it's been argued by Jürgen Blum, who's the expert in collisional physics, who did a lot of those drop tower experiments I was showing you, makes the argument that if you have violent collisions, you will simply compact planetesimals too much, the cometesimals too much, and then they won't then be able to outgas and create tails. So this is an argument for a fairly gentle process of collapsing things into planetesimals. So I promised a few words on the next step of planet formation, which is growing into cores. Is that 5 minutes went by already? Okay, good. So the comments I want to make on this is that the way terrestrial planet and core formation is typically thought of is as an era of giant impacts. And while giant impacts clearly happen, we have the moon, we have a lot of craters, there's this other possibility of what happens while the gas disk is still present, that you have small solids. Their accretion process is very different. It's one where they are sort of gradually swept onto the protoplanet with the assistance of gas drag forces. And so thinking of these two different mechanisms is something that affects sort of the key issues in the growth of solids. And the key issues, of course, are time scale and how much and mass. How much mass do you grow? So the point is that the time scale for this aerodynamic process of pebble accretion is potentially, and I say potentially because you have to have solids that are the right size, but it's potentially much faster than any other accretion process. Now, why is that? Here's a case of when you have weak drag. Without much gas drag, what happens is you have a lot of chaotic three-body dynamics. You can have some planetesimal that enters the Hill sphere. It has a close passage, but it sort of flies by, and then it can have an even closer passage, but then it can still escape, right? Whereas what we saw is with gas drag, once things sort of enter, they are sort of gradually swept onto the planet, and so instead of losing most of your objects to scattering and only accreting a small fraction of them, you can just accrete essentially everything that comes close to you, and so that's why it can be so much faster. And then there's also the mass availability issue that's key. And in standard, and this is probably going to be in the model you work on with Christoph Mordesini, in standard planetesimal accretion, there's the concept of the isolation mass, that you're locally accreting the planetesimals that are available. And so your object can thus only grow so massive so that it has a gravitational reach of sort of 7 or so Hill radii. And that mass simply isn't large enough to explain terrestrial planets or cores unless you really jack up the disk mass or do something like that. And so the point is that if you're talking about the aerodynamic accretion of these pebbles that are radially drifting in, you then have a natural way of overcoming this isolation, that objects just keep coming in. So to summarize then, planetesimal formation, it's really not as bad as Scott was saying. We know it's a process that starts with dust coagulation. It probably ends with gravitational collapse. And to bridge the meter-sized barrier in between, we need some sort of particle concentration mechanism like the streaming instability. And then I also gave you a few words on that just now. So thanks. So the great question is, so for these Kuiper belt binaries, are you sure that basically sort of spin up and fission effectively couldn't be a formation mechanism? And so basically, no, these are actually fairly widely separated, and also the effect that's responsible for that in the asteroid belt is, I believe, primarily the Yarkovsky effect. It's sort of a radiative spin-up effect. And again, obviously with radiation being so much weaker out at the Kuiper belt, that's just not thought to be relevant. Let's see. So the question for posterity, I guess, is basically when you have a giant impact like the moon-forming event, are these issues of elasticity, how important are they? So again, there the distinction I was trying to draw there is that when you have an object like the moon-forming impact, right, the Earth was already about an Earth mass. It already had a very strong gravitational field. It has, the escape speed from the Earth now is some 20 kilometers a second. So the idea is that event happens, it fragments, and a lot of the material gets reaccreted. And then obviously some of it goes into orbit around the system to form the moon. But the point is, you don't need to rely on sticking forces to explain why when massive objects collide, there's accretion and growth. It's really in the sort of strength-dominated regime, sort of below 1/10 of a kilometer or so, where you you can't appeal to gravitational capture as much, and then you need to ask these hard questions about, how does the sticking work? No. So actually the.
Sorry, can you just repeat the question?
Yeah, sorry, I was doing good at that before. So the question is, so I described this process as being something that can make things as large as hundreds of kilometers. Could it also make things as small as 1 kilometer? Go ahead and unplug that. And so so I think the highest resolution simulations that look at this the best are some recent work by Anders Johansson, where he's showing that as you go to higher and higher resolution, the largest size of the object you're making isn't changing, but you're making a broader and broader tail of smaller and smaller fragments, which then wind up dominating by number, if not by mass. And so with that, it's possible that you don't even need to appeal to fragmentation to get some of these objects in the kilometer size range. But then if you do have fragmentation, then it then becomes like you're asking this valid question: does that fragmentation compact you too much to be a comet? And that's